Okay, so this was the imperative question I did yesterday. So in this question, we can see we have a p of x function that is defined to be the sigma from 1 I equals 0 all the way to n minus 1 of ai times x to the I. So basically, for such an array of numbers, we can just think of it as this, right? Just each of the coefficient in front. So this is 1, 1, let me just do it this year. We have 1, 1.0, negative 25 divided by 2, negative 12.5, 47, 47, negative 52, negative 52. So basically, the array is just storing the numbers, and then it makes it easier because we don't have to keep the x, right? It's just its position. Um, and then we're asked in part A to write a scalar function evaluate that takes an x as a double and then returns a double. That uses a while loop to evaluate the polynomial represented by the array x. You must state your loop invariant. Max credit will be given if you do so in a way that uses n or fewer multiplications. So when I did this question, I sort of did it the dumb way. I did not do it with the maximum credit, where I use n or fewer multiplication. I sort of just kept like a variable called, let's just say y. And what I did was every time I just do y times equals x. So then I times it by that variable and plus it to my sum. So something like I would find what first my sum would be negative 52. Then I would do what I do is I have my x variable, which would just be I just do something like this form, where I just do this. This would be what I do, and I just keep a variable called y that is equal to x to the I. And then every time I just do the multiplication of that and this plus together, right? But it's not the most efficient method because I can do it this way. It's called Horner's method. And this way it keeps the multiplication down to n. Because what you can essentially do is a0 plus x times a1 plus x times a2. So then by the time that you get to it, you have all the x's you need. So then you start off from the an over here, like a n of minus 1. So how it works is that we have this defined function. We have a result which is equal to 0. Then we have a variable I, which is a dot length minus 1. This would just be where we start off. Then we just start off with the condition I greater than or equal to 0. Obviously, that's not the case, so we're going to just do result times equal x plus a of I, right? Just basically taking what's here plus this, and then just every time times x of the previous result plus that thing, right? And then we make sure that we decrease I by 1 so that we make sure that the variant becomes 0 at some point. And then later it becomes negative, so then that's not possible anymore. So the loop invariant, and at the end we return the result. So basically the loop invariant is that from the result is always equal to the sigma from j equals I plus 1 all the way to n minus 1 of aj times x to the j minus I plus 1, right? So that's just at the start of every iteration. So it's pretty straightforward, but um, thinking of the Horner's method is a bit harder, I'd say. In part B, we now wish to find one of the roots of the polynomial px equals 0. If it is observed, as in example cubic above, a0 smaller than 0 and a n minus 1 greater than 0, what can be deduced about the presence of such roots? Justify your answer. Okay, so these are the two conditions, right? So basically what we can conclude from these two conditions combined is that there's at least one positive real root for px equals 0. So why is that the case? This is kind of like the proof behind it. If we have A0 represents basically the y-intercept, right? Because it's just showing how much the function shifted by. So if A0 is smaller than 0, then it means that we have a y-intercept less than 0. So P0 at that point is smaller than 0. But however, the second condition, a of n minus 1 greater than 0, means that as x goes to infinity, a times n minus 1, x to the n minus 1 dominates the behavior. So then the function will become large and positive. Because this function is continuous by intermediate value theorem, then we have a positive root. So then if we have something negative and something positive, if we use intermediate value theorem, yeah, we have a positive root somewhere between 0 and infinity. So that's what we can know from part B. In part C, we're asked, using the function eval from part A, complete the implementation of define floor root of this thing. And then we have the required condition that evaluate 0 has to be smaller than or equal to 0 and evaluate x has to be greater than 0. So basically that is just our preconditions. And this function should return an integer approximation to a root of px. Specifically, it should return an integer x such that px smaller than or equal to 0, px plus 1, subject to the precondition that this contains the root. Explain why your function works correctly by carefully stating the invariant, variant, postcondition for any loop you write. Max credit will be given if your code makes about log 2x calls to the evaluate function. So for this, what we do is we know that we're trying to get to log 2x, right? If we're just going to do a linear search over that, there's no way we're going to get it to a log. So we know that we're going to have to split up the things. So then that kind of leads us to doing a binary search. So this would be kind of the code for it. Def floor root of x as an integer to integer. And then this is the precondition. And then we just define a variable low and a variable high as 0 and x. While the high minus low is greater than 1, so basically when it's equal to 1, we want to stop. And then we have our middle value, which is just low plus high divided by 2. And then if our evaluate middle is smaller than or equal to 0, then we just update the low. Otherwise, we update the high. And then we return the low value at the end when it's equal to 1. Right. So the loop invariant is that evaluate low is smaller than or equal to 0, smaller than evaluate high. Low is the root is between the low and high. And then the variant high minus low is decreasing as the interval is halved every iteration. And then in the post condition, the loop terminates when high minus low is equal to 1, and this guarantees that evaluate low is smaller than or equal to 0, and evaluate low is greater than 0, so root is at low. So that's kind of what we have. I think I lost point on this function because I knew that I had to do like the binary part was all right, but I think I screwed up because I forgot that the return type was in and I just treated it as double. So that's definitely something on me. But yeah, I got the right idea though. In part D, we have now write a function that's subject to conditions in part B, holding will calculate a floor root without being given the upper bound x. State the invariant variant postcondition of any loop you write. Use as few calls as evaluate to as possible. How many polynomial evaluation does your function make? Okay, so basically what I did for this, I got this part almost right. So the idea is that you just have, I wrote it as an additional function, but here in this code, the solution, we have var low is equal to 0, var high is equal to 1, and we're just going to take a while loop. While the evaluation of this is smaller than or equal to 0, we're just going to make sure that we update the low value, and then we update the high value. And then we just do it by 2 times. So then we just kind of search by 1, 2, 4, 8, 16, so on and so forth. So that we're not just searching by a constant interval. This interval kind of multiplies itself by 2 every time. And then the invariant for our loop would be that the eval low would be smaller than or equal to 0 at all times. And the post condition is that high minus low equals to 1 in the same code as before. And then the evaluation takes log 2 of x for this first part. And then the previous part, as before, would take log 2x. So in total, it would be approximately 2 log 2x evaluations. So yeah, overall this one, I think the most difficult part was actually part A, thinking of using the Horner's method. But other than that, all the other parts were relatively doable. Let's end it off here.